Okay, we can start. This is mathematics for economics, and in this lecture we are going to explain differential equation. This is differential equation we can consider is y dot equal to a real number a. So this is a differential equation which we have the derivative respect to time of a function y, which is y dot t defined as uh, dy over dt, which is the derivative of y respect to time, and we know that this derivative is equal to a real number a. This is very simple to solve because in this case the function yt will be equal to a times t plus a constant c. So the final result is a set of solution, a set of function according to a constant c. This is the general solution of this very simple differential equation. If we want a particular solution, we can impose some initial condition. For instance, the initial value of y at time 0 is equal to a certain value y0. In this case, if this is true, we know that we can substitute this value here, and we have y0 equal to a times 0 because initial value for time is equal to 0 plus the constant c. So we get c equal to y0, and the particular solution of our differential equation can be written considering the general solution and substituting c equal to y0. So the particular solution is yt equal to a times t plus y0, which means that if we want to draw this solution, so the value of y respect to time, if this is y0, this is the function yt respect is a linear respect to time. Now we consider a more interesting differential equation. Y dot t equal to, where y dot is defined as the derivative of y respect to time, equal to real parameter a times y of t plus parameter b. Now, this is a linear differential equation because it's linear in y, and we want to solve this differential equation. In this case, we can write this equation as y dot t minus a yt equal to, sorry, so we can write this equation as y dot t, so the derivative respect to time, minus a yt equal to b. In this case, we can multiply both sides by an integrating factor e to the power minus at, e to the power minus at, so it's possible to write this first side as the derivative of yt e to the power minus at respect to time equal to b e to the power minus at. This means, why this is, you can check by yourself that this first side is equal to this derivative, applying the derivative of a product between two functions. In this case, we can integrate both sides of this respect to time. We know that we can in some sense simplify this differential respect to time. The integral and differential are inverse functions, so finally we get y of t e to the power minus at equal to, we need to solve this integral. which is the solution is minus b over a e to the power of minus a t plus a constant c, because we know that the solution of an integral is a set of functions. So the general solution of this differential equation is y of t equal to minus b over a plus c, which multiply e to the power of a t. This is the general solution of the differential equation. Now, we can find the so-called steady-state solution of this differential equation, imposing that the derivative with respect to time on y is equal to 0. This means in some sense that the speed of this variable is equal to 0, so we can find the steady-state solution. This implies that applying the initial differential equation, that a y star, which is our steady-state solution, plus b is equal to 0, which means that y star, so the steady-state solution, is minus b over a divided by a. So this is the steady-state solution, is minus b over a. Now, starting from the general solution, we need some initial condition in order to find particular solution. If we assume that at time 0 y is equal to a value y0, this means substituting here that y0 is equal to minus b over a plus c, which means that c is equal to c minus is y0 plus b over a, which is equal to y0 minus y star. Now we can write the particular solution in terms of steady-state solution, because general solution was y of t equal to minus b over a plus c e to the power of a t. This is the general solution. The particular solution will be y of t equal to, we know that minus b over a is y star, plus c is y0 minus y star, which multiply e to the power of a t. This is the particular solution given the initial condition y of 0 equal to y0. This is an expression which we can see that if the initial value of our variable is other than the steady state solution, we don't know if the variable will come back to the steady state. What I mean, we can compute the limit for t going to plus infinite of yt. This limit will be equal to y star, so the steady state solution, if and only if a is smaller than 0, because in this case this limit will go to 0, so yt will converge towards y star. But this limit is equal to plus infinite if a is greater than 0. So it's not we need in order to check the stability of our steady state solution, we need to check the sign of a. If the sign is negative, so our solution, our steady state solution, will be globally stable. We can see this Also computing the derivative of y dot respect to y in our initial differential equation. This is equal to a, because the differential equation was y dot t equal to a y t plus b. So the derivative of y dot respect to y is equal to a, and we can draw the so-called, this is the so-called phase diagram, in which we have y dot respect to y. If a is greater than 0, this function will be increasing, because there the derivative is positive. This is y star, because for y equal to y star, this, this is we have steady state, so y dot will be equal to 0. But if we are here on the right, the speed is positive. This means that we will move on the right. On the contrary, if we are on the left, the speed will be negative, so we will go on the left. This means that if a is greater than 0, also in this case, we see that y star is not stable, it's globally unstable. The case in which a is smaller than 0 is when y dot respect to y is decreasing. Y star is the value of y which make the speed equal to 0, so this means steady state. If we are on the right, the speed is negative, this means that we go in this direction. If we are on the left, the speed will be positive, this means that we go in this sense. So y star, also through the phase diagram, will be globally stable if a is smaller than 0.